Last time, as I was saying, we covered what happens when you do an electrophilic aromatic substitution and there's a group already on the aromatic ring. Excellent question about last time's lecture. I did forget, but the answer to your question is it's up there now. I just now put it up. So you should find it on my YouTube channel now. I did entirely forget. Sorry about that, but I just now took care of it. And I'm going to try not to let it go as long with today's lecture. Good, so we know that if there's already a group on an aromatic ring, then we need to worry about whether it's activating or deactivating, which is almost a one-to-one correspondence with whether it's orthoparadirecting or metadirecting, respectively. Again, the only weird one is that one in the middle, which is halogens. Those are deactivating because they're electronegative, but orthoparadirecting because they are able to donate electron density by resonance due to those lone pairs. So, but the question then comes, what if there's multiple groups already on the aromatic ring? And I've tried my best, and if I do say so myself, I think I've done a reasonable job at breaking that question down for you into a step-by-step plan, at the end of which you will always be able to figure out what the major product is. As always, there can always be multiple products, but I think this way you can pick out what the major product will be and be pretty confident about it. So let's go through the cases one by one. We'll start with the simplest case. What if you do an electrophilic aromatic substitution and there's two or more groups on there, but as a result, all of the positions in the ring are equivalent? And that would be like this case here. We've got two methyl groups para to one another. By the way, you can call that guy paraxylene if you like, or p-xylene with an X, funny name. Xylene means dimethylbenzene, so you'll sometimes see that term used. I really don't care if you call it 1,4-dimethylbenzene or p-dimethylbenzene, same thing. But be that as it may, I think you'll see as a result, all of the four remaining positions on the ring are equivalent. So it doesn't matter where you put it. So if we were to do an electrophilic aromatic bromination with bromine and iron 3 bromide, well, it doesn't really matter where you put the bromine. All those positions are the same. So we can be confident that's going to be the major product. Like I said, that's the simplest case. Slightly less simple is if there's multiple substituents that are there, but they're in agreement as to where to put the new group. Now, what do I mean by that they're in agreement? Let me move that over here. So an example would be like this one over here. Here we're doing an electrophilic aromatic sulfonation, right? We've got sulfur trioxide and sulfuric acid. That's our fuming sulfuric acid. And we've got an OH group. Let me just make that guy blue. And we've got a nitro group para to it. We'll make that one red. And let's consider for a moment, oh, that's not red. That's red. Let's consider for a moment where each of those two groups wants to put the sulfonic acid group. We already know it's going to be a sulfonic acid group because of the reagents used. And again, just a reminder, it's not the reagents we use that determine where the new group goes. It's always and only any groups that are already on the benzene ring. Those are the ones that direct where the group goes. So let's consider this hydroxy group. That's going to be an orthoparadirecting group. That means it wants to put, I'll just put little X's or something like that. It wants to put the new group in one of these positions. Let me make that one blue first. That's ortho to the OH. This one over here is ortho to the OH. And of course, the para position's blocked. It already has the nitro group there. But the OH group would like to put the sulfonic acid group in one of those two equivalent places. What about the nitro group? Well, the nitro group is metadirecting. So it would like to put the new group meta to the nitro group. So I could just make those two blue X's red X's. And so as you see, these two groups are in agreement. They both want to put the sulfonic acid group on one of those two carbons, and again, it doesn't matter which. They're the same. If you put it in the other one, all you've done is flip the molecule over. It's the same thing. So that's what I mean by them being in agreement. And again, I think something you can be pretty confident about when you run into a situation like that. Let's see. What if they aren't in agreement? That's when things start to get a little bit interesting. But I think we still have a good way to come up with the answer. So again, I'll just grab that over here. And again, the principle simply is, in cases where they're not in agreement, so the substituent groups determine where the SO3H group should go, not the reagents. Exactly right. The reagents only determine what we put on. But that's exactly right. It's the substituents, not the reagents. And I'm glad you're asking that. That's something that a lot of students get confused about. We said the same thing last time when we just did one substituent group. All the reagents determined was what got put on. Right? And of course, the mechanism is the same as what we covered already. But it's the pre-existing groups that direct the new incoming group where to go. Ortho-para-directing groups are going to be the ones to direct, obviously, to ortho and para positions, and meta-directing groups to the meta position. And what determines that? Well, again, and we'll have a lot more to say about this later today also. Again, remember you've got tables in your book that will demonstrate to you, I hope, that your ortho-para-directing groups are going to be by and large electron donating, either by resonance because they have one or more lone pairs. My computer wants to update. Fine, update. Just hope it doesn't shut off the internet or something. So the ortho-para-directing groups are going to be by and large electron donating, either by resonance because you've got an atom attached to the benzene ring that has one or more lone pairs on it and can donate in electron density by resonance, or even if not, maybe you've just got an alkyl group, so there's no lone pairs there on that carbon, but you still do have an electron-rich group that's electron donating by the inductive effect. So those are going to be the ones that are ortho-para-directing. And we went over last time why that is. We gave at least two different ways of understanding why that is. And likewise, the meta-directing groups are all going to be electron withdrawing for one reason or another, either by virtue of having a plus charge directly attached to the benzene ring, like the nitrogen in the nitro group has a plus charge on it, and that's directly attached to the benzene ring. No wonder it's electron withdrawing. Or we talked about other groups that have maybe a partial plus charge on the atom directly attached to the benzene ring. What about carbonyl groups? If the carbonyl carbons directly attached to the benzene ring, we showed that carbonyl carbons have a partial plus charge because they're resonance stabilized species. So those are examples of meta-directing groups, but it all is to do with the degree of electron donation or electron withdrawing ability. And so that's all there in that in those one or two tables in the book. And again, I realize it's going to be open book in your exam. My hope, that is, if I do my job and you do your job, my hope is that you guys will come to the exam having already a good idea of where any given group falls in that scheme, if you will. And my hope would be that you can answer a question and be pretty sure of your answer, and fine, maybe go back and quickly look at that table just to make sure you're right. I said you could make a cheat sheet. Not only can you, I think that would do you much more good than just having the book and the notes available. You can, but I really think you guys will learn so much by making a cheat sheet. I would recommend that. I used to do that even when you weren't allowed to use a cheat sheet, and I think it's worthwhile. Good. So here we have a case where there's two substituent groups and they're in disagreement as to where to put the new group. I used X's before, but cheating? No clutching pearls. Just because we call it a cheat sheet doesn't mean you'll, well, actually, I guess normally a cheat sheet would be cheating, but here, since you're allowed to have extra helps, it's not cheating. Let's see then. So the methoxy group would like to put the incoming group, which I just now happened to look over. This is, of course, a Friedel-Crafts acylation. So that means we're going to put the acyl group on, in this case, a propanoyl group. So I think you'll agree, let me make the methoxy group blue so we know what we're talking about. I'll make the nitro group red. So if the methoxy group is ortho-para-directing, which we know it is, then I think you'll agree that the methoxy group would like to put the new group in one of those three places. What about the nitro group? Well, the nitro group wants to put the new group meta to itself. One of those meta positions is blocked, the methoxy group's there, but there is an available position meta to the nitro group right there. So let me make that red. So these two groups are not in agreement about where to put the new group. And so we need to determine a winner and a loser. And the winner is going to be the group that's either more activating or less deactivating. And again, an alkoxy group is going to be way more activating than an electron withdrawing group like nitro. So we can toss out this position. The nitro group's going to lose. What about the other positions that remain? Well, I think anyone, if you were just to take a wild guess, would eliminate that position since it's between the two groups. What makes the methoxy group activating again? Well, it's that it's an electron-rich group. So it has these two electron pairs. And this one happens to be electron donating by resonance by virtue of those two lone pairs. But what makes it activating is that it's an electron-rich group. And electron-rich groups will activate the ring towards electrophilic aromatic substitution. We talked about why that is last time. We gave two different rationales as to how electron donating groups make a benzene ring especially activated towards electrophilic aromatic substitution. One argument we gave based on the structure of the intermediate that you get after the initial addition. And we showed that the intermediate with addition at the ortho and para positions is much more stabilized than if you added to the meta position to an electron donating group like an alkoxy group. And the other argument we made was by the structure of the starting material itself and looking at other resonance forms just of the starting material. And we saw there that lo and behold, it's the ortho and para positions that have extra electron density on them. No wonder that's where electron donating groups want to put the new group at, in either one of the ortho positions or the para position. And again, in general, absent other information, if you were to ask me what's going to be the major product when you've got an ortho-para directing group, I would pick the para product, just because it's got more room out there. Yes, there are occasional exceptions for various reasons, but if you were to ask me to answer a question like that, that's what I would put. And I would expect that there's at least a 90 to 95% chance that I'm right. Over here, we're considering what happens when you have multiple pre-existing groups. And we've observed that these two groups are in disagreement, but the meta-directing group, the one that's more electron donating, or I'm sorry, the one that's more electron withdrawing, or the one that's more deactivating, less activating, that one's going to lose. There's always going to be one group that's more activating than the other, and I believe you will always be able to tell. It's not going to be a tie. One of the two groups is going to be either more activating or less deactivating. And that's the one that's going to win. Again, I think you will always be able to make that decision. I don't think you're going to be in a situation where you can't tell. If the two groups are different, one of them is going to be more activating and one's going to be less activating. And the one that's more activating or less deactivating is the winner. So we observed the methoxy group would like to put the new group in one of these three positions. This one here, though, doesn't make a whole lot of sense because it's between the two groups. Why would it want to do that when it can be only next to one of the groups? How can you tell which is going to be the stronger of the two? Well, again, at first, you'll know by looking at that table in the book. But I think if you work with it and practice with it, you'll begin to see the pattern. You'll begin to learn what makes something. Oh, what about, oh, that you see, here's a good question. What if, but it gives an order, I think. One of the tables gives the order. And the one that gives the order shows strengths. So for instance, if instead of methoxy and nitro, we had methoxy and a halogen, still the methoxy would win. It's more activating than the halogen. So yeah, I think if you look carefully again, you'll see it does give you a way by which you can know for sure which of any two groups is more activating than the other. And certainly by practicing with OWL, I think you'll begin to develop that experience. So in this case, it's very clear. The alkoxy group defeats the nitro group. And so again, we're not going to put the new group in between two pre-existing groups. That doesn't make sense. Why put it next to both of them when you can put it next to just one of them? So the question then becomes, having a nitro and a halogen. Well, a halogen will be more activating than the nitro group. So between nitro and halogen, the halogen would win. Halogen is also orthoparadirecting. Halogens are the only one that's weird. Remember, halogens are like right in the middle of that table. So halogens are orthoparadirecting but deactivating. They're orthoparadirecting because they have those lone pairs, and so they can donate electron density by resonance, but they're also pretty electronegative. So that's electron withdrawing by the inductive effect. So the two have some offsetting properties to each other. Anyway, would the product be most stable because it attached to the para position in relation to the methoxy group? Someone asked me that in the last class too, and it's a good question. And I think that was the first time anyone asked me that question. So there you go. I've been doing this 22, 23 years, and always someone comes up with a question I've never been asked before. I think the one-word answer to your question is no. I don't think, at least I doubt that there's any kind of trend that makes one thing always one way and one thing always another. My best understanding is the answer is no, or at least not necessarily. I don't know that it is to do with the product. I think it is to do mostly with the intermediate, more so than the product, but which we went over the last time. But be that as it may, now we need to decide, are we going to go next to the nitro group or are we going to go next to the methoxy group? How do we know where to put it? And the answer I've given you here in your class notes, let me just show you where. If in doubt, it's better to put the new group into a less hindered position than a more hindered one, other things being equal. So you want to put it next to the smaller group, not next to the bigger group. And how do you know which is bigger and which is smaller? In general, it's the one with fewer atoms that's going to be smaller. And I mean, yes, it's a bit of an oversimplification, but I in general don't think that's going to lead you astray. That's the principle I would normally use too. So methoxy is 4 atoms. Wait, 1, 2, 3, 4, 5 atoms. And nitro is 3 atoms. So we're going to want to put it next to the smaller group, the one that has fewer atoms in it. And so if you ask me what the major product would be, that would be what I would put. And I would be pretty confident that that's the right answer. And you might get some of other products as well in the product mixture, but I would bet that that's the major product. That's certainly what I would predict. So this part explains what to do when you have multiple substituents and they are in disagreement about where to direct the new group. It says that the winning group is the one that's either more activating or less deactivating, and I think you will always be able to tell that. I've not come up with a situation where you couldn't tell. And even still, by the way, I still have one to tell you about, one principle to tell you about yet, which is what to do if you still can't tell. What to do if it's still ambiguous. And I think that will take care of all of the other possibilities. So in fact, let's just go straight there. If ambiguity still exists, the major product will result from substitution at the least hindered position possible. Again, by least hindered, we've already defined that by size of the group, etc. So let's look at this compound here with the 2 ethoxy groups. And let's say that we're going to do a Friedel-Crafts alkylation with tert-butyl bromide and iron 3 bromide. Well, both of these ethoxy groups cannot win. If the new group comes in para to one of them, then it's meta to the other. If it comes in ortho to one of them, then it's meta to the other. So they cannot both win. So really, we have only 2 choices. We can either put the tert-butyl group next to one of the ethoxies, or we can put it out here so that it's para to one of them and meta to the other one. And I think it's reasonable to predict that this is going to be the major product, because there's more room for the tert-butyl group out here. It's further away from the 2 ethoxy groups. That would again be what I would predict. So you see, both ethoxy groups cannot win at the same time. Might as well put the group further away, as far away as possible. So just to take you through all of these things again, there's the situation where all available positions to put the new group are the same, so it doesn't matter. There's also the situation where you have 2 groups, but they're in agreement as to where to put the new group. That's fairly straightforward. Takes some analysis, but once you come up that they're in agreement, then it's a pretty easy decision. If they're not in agreement, then it's the group that's either more activating or less deactivating that wins. And I think you'll in general be able to tell that. But if after all this you still don't know, it's still ambiguous, then I think the best is to put the new group in as unhindered a position as possible. And I believe that you'll be able to answer any question. I don't think it's possible for either Owl or me to ask you a question where if you follow this step-by-step method, you can't know what the major product's going to be. I think it's not possible. I don't think I could do it even if I wanted to. Why not put the group in the carbon below that one? Well, that's the same thing, right? This tert-butyl is para to this ethoxy and meta to this one. If you put it over here, then it's para to this one and meta to this one. So the other way you know that is that if you just flip the molecule over, you've interchanged them. So those 2 positions are the same. So I would say the way you know it is by counting is by looking at how it's connected, how the connectivity is. And I think you'll conclude that both of those are the same. I assume you're talking about putting the tert-butyl group on this carbon. Yeah, it's the same thing, same compound. All you've done is flipped it over. Good. Well, I think that's all I have to say on that idea. Let me see where we at. 12:23. We have 25 minutes. This is good. We should have plenty of time. Good. Any other questions on multiple substituent effects? What about with 3 substituents? Same thing. Yeah, same idea. I don't think it's possible to come up with. I mean, eventually this gets stupid. So you've got 5 substituents. Well, there's only one place left, you know. Eventually it just gets a little silly, but I believe you will always be able to tell what the major product is. I honestly believe that. I drink way too much Diet Coke. Confession time. Good, well, I want to cover nucleophilic aromatic substitution today also. I do have a couple of reef pulling questions for you guys. So as usual, with your various devices, please. So 80 of the 100 points today will be from attendance. This is just the chance to get 90 or 100. First question, which of the following groups is most difficult to substitute for an aromatic hydrogen in an electrophilic aromatic substitution reaction? And we'll get that started. I'll leave that up for about 2 minutes. But I think if you look carefully at those 5 choices, 4 of those are ones we have good methods for, that we talked about a couple classes ago. One of them, not so much. So you want to pick the one that's not so much. Okay, well then, if you'll recall from a few lectures ago, we learned how to put acyl groups such as acetyl on by Friedel-Crafts acylation. And likewise, alkyl groups, at least when we're not going to have a carbocation rearrangement, by Friedel-Crafts alkylation. And of course, with a methyl group, we wouldn't have to worry about carbocation rearrangement. There's only one carbon. CH3 plus is not going to rearrange. Likewise, we learned about electrophilic aromatic nitration, nitric acid and sulfuric acid. We learned how to put a sulfonic acid group on. That's your electrophilic aromatic sulfonation with fuming sulfuric acid, SO3 and sulfuric acid. The only one that's difficult to put on, I won't say impossible, by an electrophilic aromatic substitution is OH. By the way, putting on an OH group with nucleophilic aromatic substitution turns out to be very easy. But I think the best answer to this one is B. And that's kind of what it looked like in the previous class too. Well, that's okay. Second and final question, what reagent or reagents would be used to effect the following transformation? So one of those sets of reagents is right, the other four are wrong. You want to pick the one that's right. Okay, so hopefully we're all in agreement that we've done an electrophilic aromatic nitration here. We've put on the nitro group, and hopefully you recall the reagents for putting on that nitro group are nitric acid and sulfuric acid, or in other words, E. So I think E is the best answer. Yep, you guys did too. Good, so as I said, the remaining 80 points are from attendance. I'll post that up to eCampus once I get a chance, and I'll try not to take as long with today's lecture on YouTube as well. Good, so let me do this. Let me clear some space. So, as I said, the other topic I'd like to cover today is on nucleophilic aromatic substitution. And in a process of nucleophilic aromatic substitution, we're basically going to take pretty much everything we said about electrophilic aromatic substitution and stand it on its head. It's pretty much going to be the polar opposite of electrophilic aromatic substitution, as you can tell by the name. Let me just go back to that. And as you can imagine, instead of reacting an aromatic ring with an electrophile, which is what we've done up till now, we're going to react an aromatic ring with a nucleophile. And that is possible as long as you have a leaving group in the aromatic ring, and as long as, especially I should say, if there is an electron withdrawing substituent. So, like I said, we're going to turn electrophilic aromatic substitution on its head. With electrophilic aromatic substitution, we found that electron donating groups activated the ring towards electrophilic aromatic substitution, which makes sense. You're asking the benzene ring to act as a nucleophile and to donate electron density out towards an electrophile. Small wonder that those aromatic rings that have electron-rich groups on them are going to be activated towards reacting with an electrophile. But here, the aromatic ring is going to be reacting with a nucleophile. And so now we find that electron withdrawing groups activate aromatic rings towards nucleophilic aromatic substitution. So for example, if you had something like, whoops, and we'll do at least a couple of examples of this. Let's say that you had an aromatic ring with a nitro group and some leaving group such as a halogen. Any halogen would work. Someone asked last time, could I put a tosylate on here? Would that work as well? I would think so. I mean, I'll be honest, I don't have exactly extensive personal experience with reactions of this type, but I would certainly expect so, that any kind of alkyl or aryl sulfonate would also work just fine. And so now, instead of reacting this aromatic compound with an electrophile, we're going to react it with a nucleophile. And good nucleophiles are things that I will expect that you can recognize by now. And it could be any of the good nucleophiles that we talked about in chapter 11. Certainly one example of a strongly nucleophilic solution is sodium amide in liquid ammonia. This gets back to something else, which is that, something else I always like to stress, which is that, remember that whenever you see an alkali metal salt, remember that what you're really looking at is the anion. So when you see NaNH2, you need to know that you're really looking at NH2 minus, right? The alkali metal ion, whoops. The alkali metal ion is just a spectator ion. So that's something you need to know, that when you see an alkali metal salt such as NaNH2, that to use that as our example, NaNH2 is this. The Na plus ion doesn't play any role in the chemistry. NaCN is Cn minus. KCl is Cl minus. That's one thing you have to know. And I've mentioned that I've taught Gen Chem to some degree, not quite as often as I've taught organic. But one thing I would always find is that teaching about ionic compounds is one of the hardest things, both to teach and to learn. And one thing I would always say is, it's a shame that we don't write ionic compounds like this. That would make it so much easier for students. But unfortunately, someone long, long ago decided that we would not write the charges. They're still there, but we don't write them. Someone just made that decision decades and centuries ago. And so we're stuck with it. But that's something that you need to know in order to be able to recognize good nucleophiles when you see them. And it's because they're usually provided as alkali metal salts. Now they might just write NH2 minus. You can do that. But when you are given something as an alkali metal salt, either sodium or lithium or potassium, that really when you see something like this, you need to know immediately that what you're looking at is this, that you're looking at a nucleophile. And I would expect that out of this reaction, in pretty good yield, you would get the aniline derivative, the amino substituted benzene. And of course, there's inorganic side products as well. I guess you'd get some sodium chloride. But here, this has undergone a nucleophilic aromatic substitution. And we're going to go over the mechanism in just a moment, but it's very important that you know that this reaction is neither SN2 nor SN1. It's something different from both of them. I do expect, of course, that you still know what SN2 and SN1 reactions are. We'll still run into them from time to time, but not here. This reaction is neither SN2 nor SN1. SN2 reaction would mean that it goes just in one step. And we know that's not going to happen because this carbon atom is sp2 hybridized. And we learned that sp2 hybridized carbons do not undergo SN2 reactions. An SN1 reaction would go by a carbocation intermediate. And this one's not going to do that. This is going to go through a carbanion intermediate. So we can maybe save benzene for next time. So let's think about the mechanism of this reaction. Whoops, I just screwed that up. It's not letting me do it. There we go. So the first step of a nucleophilic aromatic substitution reaction, let me also get my NH2 minus down here. The first step involves the nucleophile simply adding into the aromatic ring. And in general, it's going to like to add where the leaving group is. And again, it doesn't have to be a chlorine. It can be another halogen or a tosylate or mesylate or something like that. And we then, of course, will need to break that carbon-carbon pi bond. And you then have choices as to where to put the electron density. You can just put the electron density right on this carbon and make a carbanion, or you could show the electrons moving around to this carbon, the one with the nitro group on it, and then show the minus charge being on that carbon, that's perfectly fine. So this intermediate now will look like a little something like this. This is now NH2. And so now we'll have our carbanion on this carbon. That's perfectly fine. Or you could have shuffled the electrons around one more time and put the minus charge over here. So whether you show the carbanion being here or here or here doesn't matter. It's a resonance stabilized intermediate. And remember the rules when you're dealing with a resonance stabilized intermediate along the way in a reaction mechanism. The rules are you can use any of the resonance forms, whichever one you like, and it will always be possible to draw a correct mechanism. It just depends how you push your arrows. So if you want to show the intermediate as having the minus charge here, that's fine. Over here is fine. Over here also fine. So whenever you've got a resonance stabilized intermediate, it doesn't matter which of the resonance forms you use. That's something we'll run into quite a lot this term. Anyway, once we have that intermediate, let's see now, this is now going to push the electrons back into the aromatic ring. That will regenerate the aromaticity, for which, as you can imagine, there's an extremely strong driving force. We kick out the leaving group, whatever it might be, and that gets us straight to our product, which would look like this. So it's essentially a two-step process, but again, this is not SN2 and it is not SN1. The way you know it's not SN2 is because there's two steps, SN2 reactions of one step. And the way you know it's not SN1 is because SN1 reactions go through a carbocation. Let me see, is it like the E1CB reaction? A little bit, although that reaction involves loss of a proton. This one does not. But it's a good question. The E1CB mechanism is similar to this in that both go through a carbanion. And however, let me think now. Yeah, it's an addition plus an elimination, exactly. And actually, so is electrophilic aromatic substitution. But yes, you're exactly right. It's just that in electrophilic aromatic substitution, we need to remove a proton at the end in order to go back to an aromatic ring. Here, we need to lose our leaving group. I can also give you a little more information on this. It turns out that I just want to make absolutely certain I'm not lying to you, but I think it's the first step that's the slow step. I just want to double check you. Yes, that's right. The first step, and by the way, we'll do at least one more example of this, so don't panic, but it's the first step that's the slow step, or the rate determining step. And the second step is comparatively very fast, which one thing that I just came up with off the top of my head is that's all we need to know in order to know the rate law. If this is the rate determining step, the slow step, well, we see that there's two species involved, the aromatic compound and the nucleophile. So that tells us all we need to know. The rate law for this reaction would be rate constant times nucleophile concentration. I'm going to put times aromatic compound concentration. And that was another thing that just occurred to me for the first time ever, talking to your colleagues in my previous class. So I would be very confident that that's the rate law of this reaction. It's second order, because we see two species involved in the rate determining step. The second step is comparatively fast, and that's not surprising. We're regenerating an aromatic ring. It's a pretty tremendous driving force. So I do want to show you at least one more example of a nucleophilic aromatic substitution. We've got 7 minutes. I think that will work fine. Could you repeat what aromatic, well, by aromatic compound, I mean the starting material, whatever it is that you're starting with. Where'd it go? Yeah, I just mean whatever your aromatic starting material is. Yeah, yep. So you could put rate constant times nucleophile times starting material concentration. Fine. I think that's the same thing. Good. Well, let's do another. One other compound that, so the last step is basically reestablish the conjugation and kick out the original leaving group, not electron withdrawing group. Otherwise, perfect. But yes, you kick out the leaving group and reestablish conjugation. So again, I can't claim much personal experience with actually running nucleophilic aromatic substitution reactions, but I am told, and I believe it, that another very good substrate for nucleophilic aromatic substitution is hexafluorobenzene, which is kind of a strange compound, but you can certainly get your hands on it. As our nucleophile, maybe let's use sodium hydrosulfide. Ethanol would be a good solvent here, should dissolve everything pretty well. And so the product I would expect to get would be to replace one of the fluorines with SH. In terms of the mechanism, just like what we had before, here's our nucleophile, SH minus. Once again, the sodium counterion doesn't play any role in the chemistry. I would expect that the hydrosulfide ion will attack one of those carbons. They're all the same. And then you could show the carbanion forming on any one of the three carbons. You could put the electron density just next door here. You could put it all the way around in para to it, or in the other ortho position over here. So any of the above would be just fine. And so just give myself a little more room. I would expect the intermediate would look a little something like this. We've got SH over here, and we'll have our carbanion over here. But like I said, you don't have to put the carbanion here. There's two other choices, both of which are equally correct. Because this carbanion is resonance stabilized. There's also going to be some minus charge on this carbon and also some on that carbon. And you can draw the mechanism correctly using any of those resonance contributors. Doesn't matter. That there will certainly be a way to show the mechanism correctly. But once we have this intermediate, of course, that's once again our slow step. The reestablishment of the aromaticity is comparatively very fast. This folds back in over here to regenerate the aromaticity. We lose our leaving group. Fluoride isn't the greatest leaving group in the world, but when it comes to regenerating aromaticity, it's good enough. And so I would expect that the major product would look like that, where sulfhydryl has replaced the fluorine. Sulfur makes for very good nucleophiles, so I think that would go very easily. Someone in the previous class asked, and I'm sure you guys are wondering too, what would happen if you used multiple equivalents of sodium hydrosulfide? And I would be worried about that. I would worry if you use, like, let's say 2 equivalents, that you'd get a mixture. You'd get like some rings with 2 or 3 SHs, some with just 1, and some unreacted starting material. I would think that best practice would be using just 1 equivalent. You know, if you put in 100 equivalents, would you replace all of them? Probably. I don't know how fast that would go. I would be worried in all of the above cases that you would, in any case, get a mixture. I would be only confident of a reasonably clean product mixture if you just used one equivalent, or maybe even a teeny bit less. So, but with one equivalent, I would think it would be pretty clear that you would get the substitution happening just once like this. Now, there's another reaction that to me really falls under the same category. It's a kind of nucleophilic aromatic substitution, but it's special. It's the type that happens when you don't have any electron withdrawing groups on the aromatic ring. And in those cases, it's been experimentally determined, believe it or not, that you go through an intermediate called benzene, which sounds absolutely nuts, but it's been experimentally determined. So that's next time. We'll cover that and finish up about pretty much aromatic chemistry on Friday. So barring any questions for all the rest of you, I'll see you Friday. Would stereochemistry be considered for nucleophilic aromatic substitution? Well, when you look at the product, do you see any chiral carbons? I don't think any of them are chiral. They're all sp3 hybridized, sp2 hybridized. So there's no stereochemical issue. I think I see what you're saying. Well, in both of the examples I gave, I guess the intermediate is still achiral, because in both cases there's a plane of symmetry. One could imagine a starting material where the intermediate of this type would be chiral. That's true, but it wouldn't matter, because as soon as you do the elimination, it's gone. Good. Well, see you all on Friday then.